I'm going to get right into what's our objective. Our objective here is really to take data, and big chunks of data, analyze that data in a way that we can then use it and build that information into these interactive web-based systems that decision makers can use to make important, very difficult, often complicated decisions. And here we're focusing on actions within headwaters for both local habitats, such as brook trout. Certainly people care about brook trout, but perhaps even more importantly than trying to optimize those decisions that are made for brook trout in ways that can facilitate expansion of other species downstream. So how do we do that? This is just a big flow diagram that I'll work my way through over the next 15 minutes here, where we start with data up top, this information that then gets fed through a modeling process, and the key aspects of the statistics are really not as important as the pieces that we're able to pull from it. Our ability to separate stress and factors of stress along with natural characteristics of the habitat that might be controlling the species is really important, because ultimately we don't want to just say where animals are. We want to say where they should be but aren't because of stress, or where they might never be because of underlying natural habitat conditions just aren't suitable, even if we remove the stress. So that's a big part of this, this intermediate step of this analysis. Ultimately then, this information flows into a system, a GIS, a spatially explicit analytical system that allows us to visualize the results, that allows us to access the data sets and pull out the results and use it however we would want, to figure out how to prioritize areas. And since each of us are different in terms of what we find to be priorities, your priority might be phosphorus, someone else's priority might be smallmouth bass. How do we use a brook trout model to help make decisions about those two different priorities? Well, the system allows us to, for the user, to change that information around and come up with their own set of priorities based on their own criteria. We build into this what is referred to as quantitative scenario analysis. It makes use of the model, allows you to change the landscape, run it back through the model, and come up with a new prediction of stress and current conditions. And this is really important when it comes to climate change. So if we have a climate change scenario that we can run through the system. And then ultimately it's from this that we build our overall strategy. So let's dive right into some of the details of the Chesapeake Bay model that we built for brook trout. Starting with land cover and land use data sets, really the layers of data that get used are what everybody's used to. The only difference is we accumulate those from the local scale up to the network scale, and then the network scale up to the larger and larger watersheds. Within the Chesapeake Bay, there are 40, give or take, 40 Huck 8 watersheds, and that's what is color-coded here. As a typo there, it's 1,600 Huck 12 watersheds, so those are sub-watersheds within each other, and there's about 40. There's a lot of symmetry in the Chesapeake Bay when it comes to this. Within each of the 12-digit Huck watersheds, there's about 40 stream segments, map stream segments at the 1 to 100,000 K or 1 to 100,000 scale. And so it's 40 times 40 times 40, and as a Virginia grad, even I can do that math. We know that the engineering school of the state is not in Charlottesville. But ultimately, so this is that base layer of continuous, and it's a big data set, as you can imagine. Certainly data sets that you guys are familiar with. One of the big things we do in this process is separate the various land cover data sets into, we classify them as natural variables. So here I'm showing a map of predicted water temperatures at the stream segment scale throughout the watershed. So things like water temperature, precipitation, slope, so how steep is the stream, these are variables that we would consider natural habitat variables. Geology, there's a lot of these variables that we could classify this way. And we separate those from stressors, things like agricultural activity, and that's a map of cumulative agricultural activity in the watershed, at the map then at the segment scale. And keeping these separate allows us, once we've got the model outcome, to separate stress out as a function out of the model. The response data set comes from 5 states that intersect the Chesapeake Bay watershed. A bunch of criteria are used to cull down the data sets. We've got about 3,000 sample sites. And we're using fish data from the last 10 years. The data sets are multi-species abundance data that comes from electrofishing. So all these are standard protocols used throughout the different states. And ultimately we have a data set that has a location, has each species captured and the number of species in that. And here I'm just showing brook trout presence and absence from those sites. Okay, just really quickly on the modeling approach itself. We're essentially here predicting the occurrence of brook trout as a function of these natural habitat and stressor landscapes. The modeling system that we use is booster regression trees. It's actually really simple to run now in R. It's a very powerful approach, however. It's essentially thousands and tens of thousands of classification and regression trees that get built, and then they get averaged. And you end up with these really neat functions that are hard to visualize, but the outcome of the models is extremely powerful and efficient. We get good measures of error. We get good measures of spatial error. So where on the landscape are we failing to predict well? Don't discourage its use for hypothesis testing. So if I wanted to test a hypothesis of what is controlling brook trout in the landscape, I wouldn't use this approach, this statistic. But from the standpoint of generating good maps and good measures of controlling factors, it is really, really useful. And anybody that's interested, I'm sure, can ask lots of questions after I'm done. So what are some things that we get out of these model results? Well, the first thing is we get this table of relative influence of various landscape factors on brook trout. And so I've color-coded the green. These are characteristics that we would call natural quality. And then the reds are stress. And we can rank these. The greatest effect on brook trout distributions, not surprisingly, is average July water temperature, a measure of water temperature. The biggest control on that's a stressor is impervious cover. Then we see agricultural cover. Another thing that comes out of BRT, though, are these function plots that essentially relate brook trout, the likelihood of finding brook trout as a function of these different features. You can see it has a nonlinear component to it. What you can't see in this is that all these things do interact. The model incorporates interactions. You just can't visualize it particularly well in 2 dimensions because it is, if I've got 20 landscape variables, you can do that factorial, and that's the number of interactions that are underneath. And that's why it's so daggone powerful in the end, is because it really does get at all of those interactions. Another thing that's really powerful about this is we know that these landscape variables co-vary, and most statistical approaches do not handle that very, very well. And BRT does. It just sucks it up and runs these carts so many times that ultimately that gets averaged out. And we get a map like this, and we get a neat little score. This CV rock, this 0.924. You can think of that as a grade. So 100% can't get over 100%. Can't get lower than a 0, and 0 would be really bad. But it's a measure of the grade. So a model like this, the probability, the likelihood of brook trout presence, you're going to get and should get a really well graded model. If we did this with brook trout abundance, that CV rock score would probably drop to around 65. So, or it might even be in the 70s. So a solid C student, and it's just harder to predict abundance. But you might find a need for that. Okay, once we have the model and once we have those results, we can get a couple of very interesting measures. The first are what I refer to as the Natural Habitat Quality Index. And we define it as the expected occurrence of brook trout in the absence of stress given natural habitat features. For the model that we built, that's a function of water temperature, slope, and precipitation. Which is kind of neat if you think about it from the terms of modeling climate change, which we're in the process of doing right now. Precipitation and water temperature are expected to change. So we can model that. You can think of it as a stressor, or we can model it as its effect on its underlying natural quality for brook trout. And if we do that, we get this new map. So you can think of this as an historic distribution map, or at least the best that we could come up with given current data. So this current distribution map. And we can contrast that then with this current condition map, which I had shown earlier, and I'll show again, this expected occurrence of brook trout given natural habitat features and current levels of stress. And you can see the current map is warmer than the historic map, so that's a measure of where brook trout have been lost. If you subtract those two things together, if you simply do the math, you end up with an overall measure of stress. It's just the change in brook trout distributions that can be attributed to stress. And in this system, for the model suggests that impervious cover, agriculture, and mining are the dominant stressors. And we can show that then as cumulative stress. We refer to that as cumulative anthropogenic stressor index, or CASI. Okay, so these three things together are our best estimates of what was there historically, what's there now, and by difference then what we have lost. And it's these three things then that we can get at the heart of setting priorities and thinking about what will happen if we systematically attack that stress. Or, from a climate change, if we systematically change this map. This map becomes warmer into the future, and ultimately then that affects our prediction of current conditions. The other neat thing that we can do with the system is we can back out the stress that's related to any particular stressor. So here's the map of stress related to impervious surface, agriculture, and mining. And then ultimately these things coalesce to produce the overall stress map for brook trout in the watershed. And you can pretty well see that there's only a handful of areas where there's no stress. But that's reflected in this previous map. Okay, so just a couple of points here about the web-based decision support tool. Ultimately, it has three components. One is this visualization tool that allows us to visualize and access data sets interactively. A ranking tool that allows us to mess around with some things that we might think are important. And then ultimately a futuring tool which allows us to change the landscape, change the climate, and ask the question, what happens when this happens? Hierarchical visualization is a key part of this. How do we visualize conditions, and can we visualize conditions at different scales? Here I'm showing the Gunpowder Patapsco subwatershed, and on my far left, your far right there, that's mapping at the stream segment scale. Those are current conditions, and then we can see how that fits in the in 12-digit Hux space as well as the 8-digit Hux space. Here what I'm showing is these histograms are each of the 8-digit Hux, and it's a measure of the current brook trout fishery, so how many kilometers of brook trout fishery are in each 8-digit Huck, and how much have been lost due to stress. And they're ranked based on loss. And you can see the upper Susquehanna, this watershed here has lost, the lower Susquehanna, which is here, has lost the most, but also has very, very little current. The upper Susquehanna, interestingly, still has quite a bit left, but it's also lost a lot. Now, which one should we restore? That's up for folks to mess around with the data sets in the ranking tool to come to that conclusion. But the point is that this is the type of information that's in there and can be visualized. This is the west branch, or the upper west branch of the Susquehanna. And now what I'm showing here is each of the histograms is a separate 12-digit Huck. And so the 12-digit Hucks we can quantify the same way. How many kilometers of brook trout stream exist? How many have been lost? And then what should we do next? What I really want to focus on here for you guys sitting in Annapolis is not so much the west branch of the Susquehanna, but let's say we target these two, what we call neighborhoods, these 12-digit Hucks that we want to restore. And I've drawn circles around their general location. They're here. And we can, within those, see these very clearly, these houses that we have to restore. And let's say we then go in and do some work. Well, the key point is that we can expect downstream to capture additional brook trout habitat in that watershed. And we can get those, we can quantify that benefit downstream by doing this action here. So we restore locally 90 kilometers and ultimately get 50 kilometers back. And that's from the perspective of brook trout. Well, what if we don't have brook trout? Here we are in the gunpowder, and there's really no, all of these are headwater losses. There's really no downstream brook trout to be gained. But what if we have a smallmouth bass model in here as well, and we can quantify by doing this work, how will that affect for brook trout? How will that affect smallmouth bass habitat downstream? We don't currently have the smallmouth bass model in this, but it can ultimately be embedded. Here's a screenshot of a ranking tool. You can see this long list of things that we can put over there: mining stress, impervious stress, ag stress, dispersal barriers, that joint venture patches, spharophosphorus. We can put that as a layer in here, and we can ask the question, where will I find areas where I can get mining stress and climate or nitrogen reductions, as well as identify areas with climate resilience. So this ranking tool is designed to allow lots of different layers to be put into the decision-making process. And then ultimately the futuring tool maps out the same way. Here's the gunpowder Patapsco. We choose catchments. We say we're going to reduce percent agricultural and influence as much as possible, and we run the model and ask the question, what happens downstream? And ultimately then we put climate over this. We don't currently have the climate module, but it's under operation at the current time.